Hello, everyone. Welcome to the Robotics Colloquium. For those who don't come to this colloquium that often, we meet Fridays at this time at 1:30, so please do come. It's a public event. If you have speaker suggestions, please do let any of the robotics faculty know. We'd love to honor that. Really excited to have Jeannette Bohg here today. Jeannette is a professor at Stanford. She did her PhD at KTH, I remember your PhD thesis, and then went and was a group leader at Max Planck. Did some really fantastic work in her thesis on multimodal tensor fusion for robotics, and has continued that on and done so much more. I think what I really appreciate about Jeannette's work is that she does fundamental perception, planning, control algorithms, but also puts that on real physical systems. So hopefully we'll get to see a lot of that. And as you all know, as you start exploring the whole robotics stack, the most interesting problems lie at the intersection of different pieces: perception, prediction planning, perception and planning. And Jeannette's work really sort of exemplifies how these different components can be brought together to solve really hard problems. Jeannette will be here for the rest of the day, and I know her day is pretty packed with meetings. But if you'd like to meet with her, we'll try to find ways in which we can make that happen. But without further ado, Jeannette.
Thank you very much, Slade, for the introduction. So very happy to be invited. Thank you for inviting me. It's my second time in Seattle, actually, and I'm really happy. It's been always very sunny both times I've been here. And I've seen for the first time also Mount Rainier, right? Thank you, Byron, for telling me how to pronounce it. OK, so today's talk is going to be how to embrace uncertainty in robot manipulation as opposed to trying to get rid of it, OK? And then ignoring it in a way. So my research is basically driven by a puzzle, and that's a puzzle of why humans can so effortlessly manipulate any kind of object, like you, for example, eating these cookies right now, potentially. And it's really funny, or it's really puzzling to me why it is then so hard to actually reproduce that kind of skill on a robot. And it's really not clear of what is in that secret sauce that makes humans so amazing in this. And we really haven't figured it out on how we will enable robotic manipulation so that they can be really helpful to people in the future. So I have a few thoughts on maybe how we can achieve this. But today, I want to focus on one particular point, which I already brought up, and that's the one of we should probably embrace uncertainty. So what do I exactly mean by that? So one of the places where I typically don't publish is actually in computer vision and machine learning conferences, or very seldomly. I have very few papers on this. And I thought a little bit about that. And I think the reason for this is that in these two fields, very often, kind of success is measured in terms of accuracy. So, for example, in computer vision, this can be in terms of pixels, or like preferably maybe segmenting or labeling each pixel in the image, or in a point cloud, or maybe predicting forward in machine learning what is going to happen next, like to the absolute maximum possible accuracy. And that, of course, is a very interesting and challenging problem, and it has its own merits. And should be done. But I would also argue that total accuracy is actually maybe never achievable. Also, this total accuracy is not necessarily what a robot actually needs. And if you think about this picture, for example, where you see a kid playing with toys, you can imagine this kid basically playing around with these objects, maybe dropping them, maybe they're slipping, maybe it's trying to take one of these things and put them into the tractor or whatever, and it's not going to work, and it's just going to recover from these things. So it's really a very intricate process, but it's not probably not about maximizing accuracy, but rather on how to recover from maybe failures and how to try again. So this kind of task success here is really a function of really fumbling around, right? And I think all of us here, I mean, if you're a roboticist, you would be extremely impressed if there was a robot being able to do what the kid is probably doing here right now, right? And so I think I think if you were to take on this task of playing around with these objects and bringing them in a particular configuration, then trying to achieve total accuracy in explaining every pixel in this image actually will not necessarily give you task success. And so for this reason, I think maybe accuracy in the way maybe computer vision is thinking about it, or machine learning in terms of prediction is thinking about it, is maybe not the right goal, or as definitely not the only goal to strive for in robotics. So what do we do in robotics, right? I think in robotics what we need to do is to close fast feedback loops around really messy, high-dimensional sensory data, to actually do interpret the scene and really make very fast decisions. But I would argue that we need to accept then that we will never achieve total accuracy. And instead, I would argue that let's trade off accuracy with speed and work on methods that are maybe reactive and continuously adapt and can react to failure, instead of maybe trying to plan everything out based on the assumption that you have some perfect perception method or some perfect prediction method. I do think there is obviously learning and computer vision and machine learning methods and planning methods should be in there. But I think the focus maybe, the goal should be a bit different. And even if you take that view, there are still challenges or challenging questions. So you still have to ask yourself, so if I don't need total accuracy, like what is actually the important information? And how off can I be to still have a functioning robot? But just to summarize, like one message that I'm trying to convey in this talk is, like, if you work in robotics, you actually have to say maybe goodbye to perfectionism, as it's maybe people, in, for example, in computer vision often strive for, and or for in terms of prediction. And if you work in robotics, you really have to somewhat, I think, accept the fact that everything will be uncertain at a certain base level, and you have to somewhat embrace that chaos of this uncertainty that comes with a robot, actually. Okay, so once you accepted the fact that, oh, maybe we will never reduce uncertainty, then I think one good focus is actually on controllers and planners that can continuously adapt. And in today's talk, I want to go through 3 example projects where the focus is exactly on these kinds of things. So in the first project that I want to talk about, that project is about how 2 robots can help each other, or one robot helps another robot to learn a manipulation task better that is difficult because of all the uncertainty that comes in. And in this project, we are trying to basically funnel the uncertainty through physical fixtures. In the second project, I'm going to talk about a task and motion planning framework that we reformulate in such a way that it can actually deal with a dynamically changing environment, and where the plans are basically staying valid even though the environment changes. And in the third project, I'm going to talk about a difficult planning and perception problem, namely when you have tried to manipulate deformable objects. Okay, so these are the 3 projects. And I want to talk about, I'm going to start with the scaffolding project. As you, for those of you who work with a robot, all of you know is that actually autonomously learning robot skills is pretty challenging. So here you have these 3 tasks of peg insertion, turning a wrench, or a shallow depth insertion. So for example, something that people who assemble your phone, or you do sometimes when you put the battery into your phone, have to do. So these are pretty difficult tasks. And the way we want to approach this problem is, instead of trying to develop better perception methods or better controllers, what we're going to try here is to actually scaffold the learning process that this robot here actually has to go through. And the contribution here is that we formulate scaffolding as a 2-loop learning problem. Let me go through that part. So Actually, scaffolding is a concept from developmental learning, I believe. I don't know so much about this. I just know it's a concept there. But you can also think about all the things out there that we as people actually use to help in learning things or building things. So, for example, we use scaffolds to build buildings. Maybe to learn certain skills, for example, for riding a bike, you can use training wheels. And actually in automation and assembly, fixtures are a very common thing that you actually use to make assembly easier. But of course, all of these things are typically figured out, like how you place these fixtures, for example, is typically figured out by some smart engineers, right? And a trial and error period. So our goal here was really to construct a framework for robots to autonomously discover how to ease manipulation skill learning. And so let's take this peg insertion task as an example, right? It's pretty hard, or it's a difficult problem, especially if you don't know what exactly the geometry is and if you have noisy perception, to smoothly and efficiently insert this peg. But if you put a fixture at the right place that aligns just the right way with these basically corners of this hole, then suddenly the task actually becomes quite easy because that particular fixture funnels the uncertainty into that place, right? So basically, the fixture blocks and prevents a lot of these kind of false motion that a robot can go through. And therefore, this is basically how this funnel works, by basically restricting this motion. OK, so now what we want to automate is basically both the manipulation skill learning by this top robot and the fixture placement by the lower robot, right? And as an approach, we have this two-loop framework.
Quick
yes.
question.
Yes.
I mean, going back to your concept of training wheels, like the purpose of the training wheels is to enable you to be able to ride the bike without the training wheels.
Yes, I come to that later.
Okay.
How we get rid of the fixtures again.
Okay. And I guess the other point being that, like, peg and hole insertion, like the idea of chamfers in peg and hole insertion sort of came about to be able to create pre-images that are attractive.
Yes.
So well, we can come to that, but I guess my question would be, I'd love to understand, and you promised that you'll talk about it, like how the training wheels can be removed.
Yes, so that I would definitely address. And also the chamfers, yes, so people came up with the idea that this makes this easier, right? And just also funnels uncertainty. And by having actually this automatic process, you can actually optimize this online where it's maybe not so obvious how to place them. I mean, we selected pretty obvious problems here, right? But you could see how this could potentially be used for not so obvious problems. And I will show actually how you can remove them again and what happens then. Okay, so this is the approach. We have an inner and an outer loop, where in the outer loop you have basically this robot here in blue that tries to basically place this fixture, right? And the inner loop it takes a depth image as input that is basically from the overhead camera, as you see here in blue. And it uses that as input and then decides how to place the fixture. And then the inner loop has basically this robot that just uses some model-free RL method, not so important, to actually learn this particular manipulation task. And then basically the reward to the outer loop is on how fast the inner loop robot learns. So the faster the inner loop robot learns, the higher the reward for the outer loop.
Quick question.
Yes.
So it feels a bit like placing the fixture might almost be as hard as putting the peg in then, or?
Not so much because, we simplified this, right? First of all, we designed a fixture for this particular task, right? Then we did define the exploration space in which the fixture can actually be placed, right? But typically, the fixture placement is actually easier because at least in these tasks that we considered here, because they don't have to like tightly fit or whatever, right? So it's not such a difficult kind of context-rich task. Yeah. Yes. Okay. So how do we formulate these two loops, right? So the most interesting one here that actually also has an algorithmic contribution is the outer loop, where we use a contextual banded approach. So again, like you basically have as context the depth image, and you basically want to figure out, or you have the context, the depth image, and as action, you have the placement of this fixture. And you want to figure out for each of these actions what the expected reward is, right? You want to learn that in order to then pick the right one. So the challenge with this is that this particular Q function that we are trying to learn is actually discontinuous. So let me explain that. So we are basically trying to estimate this Q function that we approximate with, in this case, a CNN that takes in this depth image as input, as context. And then also as input, it has this action, which is basically this placement of the fixture, right? So if you have this Q function, at test time, you basically try to find the action that maximizes, given the context, the expected reward. And so in practice, what we do is we use CEM, like QT-op from the ARM-From2 paper, if you're familiar with that, where we basically sample a bunch of action, fit a Gaussian to the expected reward, and home in on this, right? So it's kind of a hack, but it works. Okay, but that's not so interesting. The actual challenge is how to learn that Q function, which I mentioned to you is discontinuous. So how does it actually, so this is kind of roughly how it looks like. So on the y-axis, you have the reward. And here on the x-axis, you have the action, which is basically the placement of the fixture. And here we're looking at this particular, at basically moving this L-shaped object to the left. And you see that there's basically insertion is not possible if the hole is covered. And you suddenly get a jump in the expected reward as soon as this L-shape is exactly aligned with this hole. And you get less if you move it away, right? So that's kind of how this Q function looks like and why it's discontinuous. And now for training, we basically use, we propose a new algorithm that is called smooth zooming algorithm. It's basically a combination of two algorithms. And let me just go through this. So this is kind of the pseudocode that I'm going to go through step by step. Again, we have this discontinuous Q function. And remember, we are going to use a banded approach. So basically what we do now is we essentially initialize a bunch of arms in this continuously valued function that discretize the space. And then for each of these, then we basically sample one of the arms or one of these covering balls. Imagine this is also higher dimensional. And then we sample one of the actions within that arm. So let's say we have selected this particular action in there and sampled a particular action. We tested it. We got a reward back. And then we basically, for each of these arms, for these bars, we maintain an average reward and the number of samples that we got. And we shrink the radius of this bar, of the covering bar, if it's multi-dimensional, dependent on the number of samples. And then you see that you actually have some space that is not covered anymore. So we continue creating new arms, basically, and continue sampling in this space. OK, so this is basically like a visualization of this algorithm for learning this discontinuous Q function. OK, so now the inner loop is maybe kind of less interesting, but still important to know about. So basically, the inner arm is providing the reward to the outer loop by actually learning this manipulation task. And here we use A3C, just like a model-free RL method. And one thing, of course, we wanted to know, like, OK, is it actually faster for the second robot to learn this manipulation task if the fixture is placed in the right way? And here are basically a bunch of learning curves for all of these three tasks that we consider. Maybe let's look at the peg insertion one. So you see in the orange curve there that if the fixture is placed in exactly the right place, the learning curve is basically much steeper, so it learns much faster on how to do it. And then if you have a suboptimal placement or no fixture, it takes much longer actually to learn this task. And there's a similar story with the other task. Okay, so now we went through this two-loop approach of having the outer loop with the multi-banded and the inner loop that provides the reward, basically based on how fast it learns. And if we put this together, here's a visualization of how this learned QMAP actually looks like for a fixture post-selection than a test time, right? So, so here, for example, you have these are 3 pictures for this particular orientation of this peg. And you see that you are expecting a high reward if basically this fixture is placed in such a way that it's easier for the robot to place it, right? So
quick clarifying question.
Yeah.
So you talked about the reward being how easy it is for it to learn.
Yes.
But I guess you're motivated uncertainty by saying how easy is it for it to execute. How are they correlated?
Well, that's a good question.
Hard to execute, hard to learn, easier to execute.
Right. So I guess how easy it is to learn and the learning curve you see based on, the learning curve is basically the success rate, right? Which means that early on, the robot has a higher success rate, right? Which indicates that it's also easier to actually execute this particular task, right? Basically you have the exploration space cut physically actually by these fixtures. So therefore the task becomes easier.
I guess that's a testable hypothesis.
Right.
Okay.
I guess the task becomes easier. Well, it becomes easier because you can't even if you do a wrong motion against the fixture, you won't actually go there, right? And assuming that the fixture is placed in the right way, that means your only escape route is either downward or backwards, right? So it's literally like the space of wrong motion is basically reduced. So therefore, it should be easier to do the task as well.
This is I completely understand that that's the case here, right?
Yeah.
But that's not a generalizable statement, right?
A generalizable statement. Okay.
You can compute
fine.
minima, easier minima, harder minima, easier. Like the
Okay.
One is a question
Yes.
around the ability to find the basin of attraction. The other is a question around the stability of that attraction. Like you could have a shallow minima that are unstable. But yeah, I see the point that like for this particular case.
for this particular case, okay. But I agree with you, it's not generalizable. Was there a question as well?
Is the robot that holds the fixture stiff, or is it compliant? Because if it would be compliant, it would still, if it's a bit off.
Yeah, we control this pretty stiffly. Yeah.
It can't, if it's covered a little bit of the hole, it won't allow it to still go in
I
there.
think in practice there is some movement, but it's still small enough for this to have an effect.
Okay.
Yeah. And really, we don't need another robot. I'm going to show you a video. Actually, let me show you this video, okay? So this is why we need the robot, because we can just let it run, but really you could just have a person here, right, or some other way. It's just cute to have a robot help the other robot.
So you're just showing what it was hallucinating.
Yeah, so this was actually doing the CAM.
Okay.
So literally it had the Q map, it had the Q map basically learned, and then now it's sampling it, fitting the Gaussian, sampling it again. And these are this is for the 3 tasks that you're seeing right now, right? So this task is also easier because now you can't have the wrong orientation, right? And here this is a bit more complex of a manipulation task because there are 2 steps, rotating it and then kind of sliding out. So also in this case, the battery can't move up here. Right, but sorry, your question was if it was stiffly controlled, right? Like, yeah, definitely has pretty stiff gains to not give it. Yeah. Okay, so one thing I wanted to also show is that it can actually generalize over peg geometry. So again, we have trained this policy on the square peg, and now we just reuse exactly the same one for these other peg geometries. And because it's kind of a similar structure of the problem, which will actually work. Also, this was only trained in simulation, by the way, and we just replay it, which was kind of surprising to us that it worked so well.
Small question. Did you constrain how long you would run the inner loop RL?
Yes, there was a maximum time.
That would be smaller than if you just train, like in your plot where you show that the performance and learning curves.
Yeah.
And that RL was trained probably much longer and learned much slower.
Sorry, I didn't quite understand the question. So can you repeat it?
So it appears that there were many times that outer loop would be caught, and then they would then invoke the inner loop RL. I'm just wondering, like, how long then, like, each inner loop RL would take? Because if each inner loop RL would still take a long time, because if your pack placement was just unlucky and it prevents the task from completing, then it take a long time. And then
there is a maximum time we run it, and then basically the reward is the success rate of this policy, right? At that stopping time, so that it doesn't run forever, right? And then we sample a new, during training we sample a new arm basically in this bandit approach.
So the hope is that if the placement is good, then within this limited time you would already be able to solve the task.
Yes, exactly. Okay, so just to summarize this first project, basically the main idea was here to learn to place physical fixtures to funnel uncertainty, and which is an idea that has been had, right, in automation, but there it's typically engineered. So we also made an algorithmic contribution here, which is this particular algorithm for learning this discontinuous Q function. And the result is that really if you have the fixture placed optimally, then actually the learning of this manipulation task is dramatically sped up.
Quick question about that. So you're comparing like having a scaffold, and if it's like optimal or slightly suboptimal, it does speed up learning.
Yeah.
But then you have to do a lot of learning in order to learn like the scaffold placement. So like is that then a lot slower than learning without the scaffold? Just doing the task?
That's a good question. Well, I guess the good thing is that once you have the scaffold there, you can use it for, as I showed, right? You can actually generalize it to many different things. Also, we did learn that in simulation, and it did generalize as is to the real world. It's probably longer if you have to learn for all the fixtures. For all the fixture placement in total. But because it's a physical reduction of the possible actions that you can actually do and of the failure modes, it actually works pretty well in the real world as well.
Why do we even need to learn the fixture location, right? That's something you can pretty much infer from geometry.
Okay, obviously we made like really nice fixtures that are clearly really useful for this task, right? And we did constrain the exploration space for these fixtures as well, right? And yes, for these tasks, like I look at this, I know exactly what to do, right? But just imagine tasks that are maybe not so obvious, right? And then it could be interesting to first maybe given a fixture to have basically a method figure this out autonomously, right? And also we didn't actually assume that we know anything about the geometry here. That's maybe another thing that I should mention. We didn't let the robot know anything about the squareness of the peg. Okay, but one question that I actually had as a backup slide was about what happens if you take this fixture away. Let me just go there. Exactly as Sid said, right? Like the goal of putting the training wheels is then to actually take them away again. And so we wanted to know, okay, if we take now this policy that was learned with exploiting the fixture, is it still going to work? And it's not. So if you just remove the fixture as is and actually then maybe try to train again to do it without a fixture, it actually doesn't work so well. So what we did instead, or what we tried instead, is like, okay, what happens if we actually, instead of the physical fixture, use a potential field that is virtual and place it at this optimal position while we are also removing the fixture. And then you can actually start adapting to the case where you don't have these training wheels anymore, in this case, the fixtures, with a potential field. So we found this was actually pretty interesting because now you have a virtual fixture, so you don't even need another robot. You don't even need a physical item that you maybe have to print again or whatever. You can actually play around in simulation with the geometry of these potential fields to see what is actually a good geometry, for example, for a fixture. And this is pretty cheap now to play around if it's virtual, right? So this is a pretty interesting direction for us as well. Does that answer your question?
Yeah, and again, like I think that it's interesting that it works here, right? And I guess another way of thinking about your potential field might be that it's a set of subjective priors on the policies that would work, right? I'm also curious why the potential field would not be symmetric. Like, I mean, you have an L-shaped fixture where it's really like the value is.
Yes. I mean, this was kind of like an initial experiment. We just wanted to know, okay, like exactly as you said, right? Like usually you want to remove this fixture as well, right? Okay, how do we do this? And this was more like an initial experiment, right? But I think it's interesting to now explore, okay, how can you optimize over the geometry as well, which we haven't done, right?
No, it's really interesting. I mean,
Yeah.
I think there's this problem around like Lagrangian relaxation, for example, to solve constraint optimization problems, where you put a big barrier and then you sort of relax the barrier over time. And one can imagine what you're doing here to be like a physical version of that. Like you put the barrier in place and then you sort of soften that.
Yes.
But I guess the curiosity I had was that like the history of sort of peg and hole insertion, the way you solve the peg and hole problem is like you do the deliberate miss, then you slide it in, and then you move something, and then you jiggle it in.
Yeah.
So, and then you have this remote center of compliance. So it is quite fascinating that like this works without it. But you can imagine cases where you remove the training wheels and you need to sort of relearn a different policy.
Right. Oh, I see what you mean. So you would have expected this to maybe actually find a completely different strategy.
For example.
Yeah.
Right? Yeah.
Yes.
And I think that part of it is in the ingenuity of the fixture design. Like clearly, when my kids are learning to ride their bike with their training wheels, when the training wheels come off, they don't have to like relearn the new strategy.
Yeah.
So it is remarkable to me that we can design fixtures that, when they're removed, the true policy lies within that class.
Yeah, that's
which
true.
is interesting.
Yeah. Yeah. So I think this was like an initial idea, right, just to see like what the effect is, and I think it opened some really interesting questions that you are also bringing up. Like right now, if you have this policy that does exploit it, does the policy without the fixture actually lie somewhere close to that one? Maybe not, right? And we found actually that it's not. That's why we left this potential field in there, right? So, but there's some interesting questions.
Does this allow you to kind of add noise into your motor movements and still recover the feature set, right? So humans are
What's the feature set?
So recover the policy, right? So humans are really bad at being accurate at movements, but if you go to a carpentry shop, we use fixtures all the time to replicate it, so we can use our noisy movements to still get precise features. Can you do the same thing here, where you basically can just add noise into your motor signal and still get
basically,
behavior?
we use a real robot. That means there's noise in the motor signal, right?
Right, but can you like up the noise even beyond what the real robot would do?
I think actually with this physical fixture, I think you can. Yeah. It's not that we tested this because especially, actually this upper one is a Franca, which is pretty good, but the lower one is a really crappy Kinova. I'm sorry. Like, Sid, we should also talk about that new Kinova, which I'm really disappointed by.
I take all the blame for,
No, you shouldn't. We can just commiserate maybe or something. Anyway, I don't want to blame anyone except for maybe Kinova. Okay. All right, so I had a summary, right? Let's maybe move on to the other two projects. So we talked about this one, was the automatic or learning how to scaffold. Now let's talk about a different problem where we want to do task and motion planning, and the scene is actually changing. And you want to, of course, always execute it in the real world with lots of noise and uncertainty. Okay, so let's look at this. So this is an example that is actually turned up in Marc Toussaint's work from RSS 2018, more or less. So you basically have this robot. It wants to place the small box on the large box, but the problem is that the small box is actually outside of the workspace. So it can figure out by combining symbolic and geometric reasoning that it can use this hook to actually get the little box closer and then reach for the box and place it on this shelf, right? But now, what happens if you have actually moving targets? So here, Toki is actually, moving these things around, moving the little box around. And of course, we still don't want the robot to throw its hands up and just give up, right? It should actually be able to adapt and still actually execute that, that particular plan, right? Okay, so that's the problem we want to solve. We basically adapt this particular approach from Marc Toussaint's work from RSS 2018. That is logic geometric programming, and we take it and we reformulate it to be able to do what I just showed you. So I just want to quickly go through this optimization problem, which basically just combines a logic planner with a motion optimizer, okay? Essentially, here we have the terminal cost in the objective function, and here we have this trajectory cost, looks pretty standard, and the x and the u here, these are the continuous state and actions, right? So in Marc's work, this was, for example, the joint angles and whatever, the joint velocity or accelerations that you sent. And then here you have all the constraints. So for example, this is the continuous system dynamics, which actually changes based on this discrete state that comes from this logic planner. It's like a manipulation primitive. And we also have a discrete action here, this A. So basically, this continuous system dynamics changes depending on the discrete state. And also, this particular constraint describes how the instantaneous system dynamics are when the discrete action AK here actually changes. Okay. So, and this is basically kind of coming from the logic plan, right? So you are in a particular state of the system, a discrete state. You take a action primitive, and then you end up in the next successor state. So, okay. So this is this particular optimization problem down here that basically Mike proposed in his paper. And for the logic plan, he just uses something called strips planning, which basically has a bunch of proposition and actions that have pre- and post conditions, a bunch of objects and initial states and a goal. And then given these particular predicates and everything, you can essentially plan out with this tree a logical plan, okay? So this is something we actually adopted and we didn't change. So we just used that. But what we did change was the way the trajectory optimization actually works with this. So this is the formulation that basically Marc used in this paper. And here it's basically the objective function is the sum of the trajectory cost across all time steps. And that basically results in a banded Hessian that can be inverted efficiently and has nice properties. The constraint functions, though, as you see here, they depend on the entire trajectory. And that makes it pretty complex and couples them in time. And the main problem here with this approach that we see is that actually once you plan the trajectory in joint space and the environment changes, you basically have to replan again, right, completely. It's going to be invalid. So we really thought about that problem, like how can we deal with this dynamic environment? And we reformulated this approach. Instead of with joint angles, we are actually using relative Cartesian frames instead. So for example, here, so what we basically wanted to achieve is to decouple the constraints that are now not coupled over time anymore. So what do we have here? Here, for example, I've shown like 2 steps in this plan. We have this arm. The next steps I want to do is to actually grasp this box. So therefore, it wants to control the end effector, the origin is here, and align that basically with the target box, okay? And then once it does that, it wants to put it on the little shelf. So now it wants to control actually this particular box frame and put it in some position relative to this little shelf, okay, somewhere. So the nice thing here, the way this is decoupled is that, when an actual robot is grasping this, it's not going to be sitting nicely in that arm in exactly the way you wanted it. No, it's going to be like in a really weird way. So, but that doesn't really matter. The way you pick this object up doesn't really matter if your target is defined in terms of relative frames relative to this target frame. Okay, so if you only control the box relative to this box, then it doesn't matter how you have grasped that box. Right, so that's basically what we exploit here in this new formulation, and how we get rid of basically this problem that if the environment changes, you have to replan. So essentially, this is how our optimization problem looks like, where we essentially plan a sequence of key relative Cartesian frames relative to the different frames of the objects in the scene that we are looking at. So this psi here is basically these relative Cartesian frames.
Quick clarifying question. It makes a lot of sense. There are certain things that can't be converted to relative Cartesian frames. Like for example, in workspace, like that depends on the corner frame of the robot. How do you address that?
Yeah. So that's true. So by getting rid of the joint state, for example, we also can't deal so easily with the joint limits, right. Which is annoying. And with the workspace, that's something we do in the symbolic planner right now, right? So the constraints of that are basically encoded there. We don't deal with the joint limits, for example, or with the singularities or whatever. Okay, so let me show you the full system. It's actually an interesting question. Which layer is taking care of what, right? There's not a black and white answer here, but here's what we did, okay? So we basically have a planning execution layer that is interleaved like that. So we have the symbolic planner that does the strips planning and produces this action skeleton. And then we have this frame optimizer, right, that plans the sequence of keyframes of Cartesian frames. Then what we do is we actually use a reactive controller that, in our case, we just use an operational space controller that basically just tries to align the n effector to the box, or tries to align the box frame to that, to bring it to that desired relative Cartesian frame, essentially, right? And now that means that if the environment changes, these relative frames that are attached to these moving objects are still exactly valid, and therefore the plan is still valid. So essentially we do the strips planning once, we keep it fixed, then we also optimize once these keyframes of Cartesian frames, and then we just use a reactive controller that continuously adapts to these movements, right? And we control this in a kilohertz. So now what would be nice, and which is something we haven't done yet, is if we basically maybe, when the environment changes, determine like, oh, actually we want a different Cartesian frame. We maybe want to replan because this and that condition changed. Or we want to say, oh, actually we want a different symbolic plan, right? So these kind of things we haven't yet addressed. It's kind of one of the open questions. Does that answer your question? Okay.
I thought you had done both of those, so it's good that.
Yeah.
Now it makes sense to me.
Yeah, so this we haven't yet addressed, but it's a very interesting question to look at this. But so here's basically what comes out, right? So here you have the Tower of Hanoi system, and because we use the strips run, we actually get multiple possible solutions out. And then, of course, the Cartesian frames are adapted to this. Here, nothing, I mean, you know how this is going to finish. And I already showed you this, right, where now that we have this optimization of all these relative Cartesian frames, the plan stays valid even if things are moving around. And of course, we also wanted to see how this now actually works in the real world. So we do have, we basically implemented or integrated this entire system on a real robot with a model-based tracker. And we had to actually combine it with markers in order to make it robust. So both of them were necessary. So there's some work to be done there. But essentially, we can show here that even if we perturb the objects and everything, this plan still works out. All right. All right. Yeah, just to summarize this particular approach. So here, the main idea, so basically what we wanted to achieve, right, is to have a planner and, or a task and motion planner that actually has a valid plan even if the object or the environment changes. And the main idea was here to optimize relative Cartesian frames. And the algorithmic contribution here was to essentially reformulate this trajectory optimization problem in terms of these frames. And therefore, we achieved this task and motion planning in dynamic environments. And I think I'm actually out of time. So I don't think I'm going to talk in detail about this particular project on manipulating deformable objects. So I'm just going to really briefly maybe talk about this. Essentially, what we wanted to achieve is a robot that can basically bring an object like this that has a very high-dimensional state space into a goal image. And we wanted this system to be robust to occlusion. So you see the robot is actually occluding the object. And this goal image isn't even of the same appearance as the object that is being manipulated here. And we have all these annoying sources of uncertainty, and we want to be able to solve it with our system. There's lots of annoying dynamics that are difficult to model. So we essentially had an approach using receding horizon control. Basically, we used MPPI for planning out how to do this manipulation. And the main contribution here was really the perception model, which means you basically have to perceive a 64-dimensional state. And it's pretty amazing because it can solve all of these difficult situations. And it can even deal with intersections and everything. And if you are interested in finding out how this actually works, then you can look at this paper. So you've already seen this. But essentially under the hood is we represent this object in state space, this linear deformable object. And we propose a differentiable renderer that allows us to do self-supervised learning and robust state estimation. And then we have basically an entire system that can do this manipulation part. OK, so with this, I just want to close. So I showed you at least 2 of these projects in detail and just kind of wishy-washied over this one. And basically, in these 3 projects, I really tried to impress on you that maybe instead of dealing with much better perception methods or much better prediction methods, maybe we just have to accept that these will never be perfect and then shift the focus towards other solutions on how to deal with the uncertainty that is always going to be there in the system. Yeah, so that is pretty much what I wanted to say. Thank you very much for your attention. These are all the students who did all this amazing work, and these are my funding sources. Thank you.
So you said the novelty is really representing this rope as 64-dimensional state. If state estimation is imperfect in that sense, like how does the rest of the framework deal with that?
Yeah, so I would say it's a bit hard to argue that this is a contribution because representing something in the physically interpretable state space has basically been done all the time. But it's more that we chose to take that representation in a physical, meaningful space of this configuration of the rope. And then what this allowed us is to use an interpretable dynamics model from a physics simulator. It allowed us to easily compute a cost between the goal state and the current state. And then the contribution was really in this perception model. So I wouldn't say that our contribution is that we chose to represent that in state space. But what was your, sorry, I forgot actually your question.
Yeah, my question is if the perceptual
Right,
model
if there's
is imperfect,
noise.
like, yeah.
Right, so the way we deal with this is basically by the top level part, right? By using a receding horizon controller, essentially. Or this is basically an MPC model where we say, okay, we just want to plan an optimal sequence of action over a certain horizon. We only execute the first part because we know perception is going to be imperfect, and there's probably going to be errors. And then we check what actually happens and replan, right? So, and this part up there is relatively easy to do because we chose to do an interpretable state representation or use that.
And you trained the perception model then in a supervised way?
Yeah, so what we did was a two-stage process where we first trained it in simulation because that's easy, but then of course this doesn't transfer to the real world. So what we did there was like a pretty, I couldn't talk about this. It's basically a self-supervised way to learn from real examples. So the robot is essentially playing around with this rope and uses the model that was trained in simulation to get a rough idea of what the configuration is, and then fine-tunes, uses a differentiable renderer basically to improve the labeling of these play data, if you want, and then uses that to fine-tune the model as well. So basically, there is some process where the entire system does automatic labeling and then retrains to actually work in the real world.
So the render more or less kind of matches the internal model then to the observations or so?
Yeah, basically, it looks kind of like that, where we have basically this input image, and the perception networks give us an initial estimate. We render this initial estimate, and then find a model basically of how this looks like, label again the image based on this model, and then we compute an image space loss to basically backpropagate to the rope and basically improve this, or to actually fine-tune the perception network. And this part here is basically independent of the actual appearance of the color. It's like transient parameters that are actually being estimated based on whatever data it sees. So that's why it works with the green background and the white rope and the red rope on the white background and all of these things. Yeah, so that's kind of roughly how it looks like.
Were there motivating domains for this work?
What are the motivating domains? So any kind of thing you want to do with a rope, for example. Maybe you want to do suturing in automatic. I mean, this is pretty far out, to be honest, but that could be a long-term vision towards this. So we haven't really looked at knotting yet. That is something we are going to do now. But any kind of thing you want to do in a household where you want to rope something together. Also, we want to go towards two-dimensional objects that are not just ropes, right? And try to see if we can extend this towards, and then you can think of folding. Yeah, these are kind of the applications.
Cool. Thank you so much.
Thank you.